Everybody all right?
Dr. Brian,
Yeah.
so over here we have B, D bar.
Yes.
Could we tie one of those inputs to high, or does it just need to be only the variable coming?
Oh, this one here,
Yes.
I could have taken B in and D in, and taken the other two inputs to high.
Okay.
It would not matter. So we've talked about implementing logic functions with logic gates. Now, how am I physically going to make a gate? I could do this with lots of things. I could have a gate here. And what have I drawn on the board? A 2-input AND gate. Everybody all right? Okay. So you know the logic function this does. If these guys are 0, 0, what do you get out? 0, 1 or 1, 0? 1, 1? Okay. Well, this is all, right now, this has just been a conceptual thing. What's a 0? What's a 1? Well, I could tell you that the physical attributes are pressure. Okay? That 4 psi is going to correspond to logic level 1. And 0 psi is equal to logic level 0. What's the blood pressure of a human?
Ideally, 120 over 80.
120 over 80-ish or something like that? How many psi is it? It's not a lot, it's a couple psi. Okay, how much pressure do you put in there? Car tires? 30, 30-ish. Road bike, 110, 120 psi. All right. Okay, so I could say 4 psi, that pressure is going to be correspond to my logic 1, and that is 0 psi would correspond to 0. Seem okay, right? I could do it the other way around. I could say 0 psi is logic level 1, and 4 psi is logic level 0. I could say minus 20 psi, a vacuum is logic level 1, and minus 50 psi is logic level 0. It's just a physical attribute. So we've got pressure. What's the other thing that you, kind of the other variable that's going to go along with pressure? Well, let's go back to an electrical system. What would you correspond pressure to? Seems voltage. I could do either one, but the most obvious is voltage. What's the other electrical variable? Okay. Now, my first question. If pressure is one of our attributes of our physical system, what's the other one? Force. Flow. Flow of something. Okay, this could be a water tower. This could be the air in your tire. I mean, so you got a pressure, you got flow to worry about. So you always have to worry about both of those things. Is that okay? All right. So, what happens if you have a little CO2 canister? You know, any of you has shot air rifles or anything, do you know what a CO2 canister is? Yes, no? How many don't? Little canister. About like this. Yeah. So how much PSI is it? Fair amount. Probably easily, probably 200 PSI. That if you puncture it, you know, you actually get a stream of compressed oxygen or room air coming out because it's so compressed that it liquefies it. Well, if I take this guy here, it's probably even higher than that, I don't know, 200, 300 PSI, something like that. And I hook that to your car tire. Are you going to be able to inflate your flat car tire to 30 PSI?
No,
Why not?
not enough volume.
There's not enough volume in there, right? So you have, whenever you hook two systems up, you have to pay attention. I went over this time and time again in 402, right? You have to always take into account loading and how, when you interface things, they interact. Okay. So if we had a pressure system here, you would have to be concerned about what? What kind of flow would be associated with that? In an ideal world, if I said that I'm going to put 4 PSI there, 4 PSI there, how much flow would you like to have coming out of this, of whatever's driving this gate?
4.
4 PSI going in. How much flow would you like to have or want to maintain that pressure? Say it. 0. Why? Because you would lose your pressure, right? So you would like to have 0 flow going in. So what would come out here? I mean, in terms of a variable, 1 or 0. Therefore, that you would expect this. If this is then going to drive other gates, would you like to have 2 PSI coming out to represent R1? You'd like to have what? 4. Okay. Would you like to have 104 coming out? No, because it might blow the other gates that you connected to, right? Is that all right? Yeah.
If we want 0 flow coming out to like maintain the pressure, then why are we putting 4 PSI coming out, which corresponds to 1?
Restate your question.
Like, okay, so max said we want 0 flow because we're maintaining the pressure. Then how come we're like
Now, are you talking input or are you talking output?
output?
Wonderful. I've got an output now. Do I want 0 flow out of it, or would I like to have a fire hose worth of flow?
Somewhere in between.
This is binary class. 0 flow or a fire hose worth of flow? Wrong. Wait a minute. Okay. We've got a balloon out here. Uninflated balloon. I'm now going to connect my output up to that balloon. It was previously at 0 PSI, yes? Okay. What's going to happen after I connect up my logic gate to this balloon? It's going to blow up, yes? Are you going to have to put air into it? So do you want some flow out? Yes. So my ideal gate, if I'm having an ideal gate, it would take no flow to establish the pressures on the input. But on the output, I could drive any flow I needed to make it work. For example, my balloon, I'm going to puff up my balloon here, and so it's going to blow up to 4 psi, right? And I want to maintain that, yes? But my stupid balloon has got a hole in it. It's got a pinhole in it. Therefore, what has to happen if I'm still going to maintain that 4 psi?
Constant flow.
You got to keep putting more air in. So, is this a good load? What would we like our loads to be?
Not needless.
Not infinite input impedance, if you will, right? No flow. Now, this is a really good analogy because you understand that if I have a sealed balloon there, how much flow is going to come out of this gate to maintain the 4 psi? 0 in steady state. But I had to put some out to get it to blow up. Everybody understand the analogy here?
So
Yes.
for our initial, like, flow on the output side, it's whatever we need it to be to maintain whatever's at the end. But then, like, for example, on the other side of the balloon, if we want to maintain the pressure, there's no flow coming out. There's no hole.
We would like that, but there may be a hole.
Okay. But if that's ideal, it would.
That's correct. And that's exactly what we're going to see on some of our gates. All right, so let's go back here now. I used PSI and flow as the analogy. This is going to be the physical entities by which we're going to represent a 0 and a 1. Do you want to make your gates out of a system like this? No. Right. You don't want to use a physical system like this. Too much piping, too heavy, whatever. Okay. So we would rather make it out of what? An electrical system. Right. And now for our electrical system, we're going to, we could have current as the variable. Okay, X amount of current going in is the logic level 1, X amount of current coming out, a logic level 0 or no current. But it's more straightforward to go ahead and consider voltage as our input. But the corollary of that is what? That something has to do what? Flow, right? So current has to flow. Everybody okay with this? Yes? All right. So we like to be able to make our devices out of electrical entities. Why? Because we want to make them itty-bitty and tiny. So we're going to use voltage to correspond to our logic level. And typically, we're going to use 5 volts to correspond to a 1 and 0 volts corresponding to a 0. This is going to be our positive logic. We certainly could come up with what we call negative logic, where 5 would equal 0 and 0 volts would equal logic level 1. But this is positive logic. Okay, because there is voltage, what's the other thing that we got to worry about? Current. So for an ideal gate, current in would be what?
0.
0. Okay, it would not take any current to make it happen. This one's going to be tricky. How about the output current? Say that again?
Whatever we needed.
Exactly. Whatever we need. Okay. We don't want a specific current out. And in fact, we would like the current out to be what?
What do you like in the steady state?
Yeah, what would I like the steady state current to be coming out to maintain a logic level 1 or a logic level 0?
0.
0. Why?
Because if it's already at the desired output, there's no need to change it.
Yeah, but I'm looking for something else. That's true.
Power consumption.
Power consumption. Okay. We would like to have the power consumption to be 0. We would like it to be 0 so that we end up with 0 watts out. Okay. Now, there's a couple of things that are going to take place here, and that's that if I have 0 current out, 0 current in, okay, in other words, if I connect this gate to other gates that are just as good as it is, and they require no steady state current, is the power consumption 0? Well, the answer is it depends. This thing may take some power to run itself. Okay, so you'd have to supply that power. Even though it's not delivering any power, not taking any power in, just to run it may take some power. So we'd have to be cautious of that. So when we are rating our gates, when we're taking a look at these physical gates, we want to take a look at the logic levels, and we want to take a look at current flow and power.
So if we were putting power into the gate, wouldn't there still be a current coming in then?
If it required current, then yes, something would consume power driving the inputs on.
So you're saying that you want the current out to be 0, right?
We would like it to be,
But I thought we would also like to do whatever is needed for the
of
next
course.
gate.
In other words, I'm saying that the gates that I'm tying it to are really, really good gates, and they don't require any current
Oh,
in
okay.
steady state. Now, we're going to find out that even though we have these almost ideal gates, it's going to be like the balloon analogy that doesn't have a leak. It's still going to take a little bit of flow to get them pressurized and to blow them up. What variable, electrical variable, would that correspond to? And you only got 3 choices.
Resistance.
Not resistance. Now you have 2 choices. Passive elements. What are the passive